The first thing you'll have to do is just simplify your radicals, all right? And so what this means is you're going to have to use like factor tree, take out everything according to your index, and then go from there. So this index is a 2. So I'm going to use my factor tree here, and I'm just going to factor it. I usually factor with a small prime. And so when I do this, I go back and say, well, 11 divided by 2 is 5. Why is it doing that? With the remainder of 1, 12 divided by 2 is 6. And I just go from there. We're going to leave the k alone for right now. All right, so since my index is 2, I'm going to group everything that is in groups of 2. So that is a group of 2 that can come out. This is a group of 2 that can come out. Nope, I'm going ahead of myself. And then this is not grouped. That's going to stay in. And then I look at my variables. If your exponent on your variable is less than your index, they're all going to stay in. But the rule is that I show you, take your index divided by, your exponent divided by your index. 2 goes into 1 0 times with a remainder of 1. So that means one of your k's is going to stay in. And then to simplify it, just multiply everything that's on the outside, multiply everything that's on the inside. And that is your answer. All right, so when I have something like number 8, I already have something on the outside. So that's already going to be on the outside down here. And then I'm going to use my factor tree exactly the way I did before. Again, you can use a small, like if I know it's even, I can use 2. 3 divided by 2 is 1 with the remainder of 1. 19 divided by 2 is 9. 12 divided by 2 is 6. So you can just do it like that all the way down until you get to all primes, which is what we're looking to do here. All right, so for my numbers, again, I'm going to look at anything that pairs up is going to come out. So I have a group of 2s that pair up. I have a group of 7s that pair up. And then I have this 2 right here that does not pair up with anything. So that's going to go on the inside. And then again, I can look at my variables. This is a to the 4th power. I'm going to take that 4 and divide it by my index, which was 2. 4 divided by 2 is 2 with a remainder of 0. So that means 2 of my a's come out, no a's stay in. And then again, to simplify it, I'm going to multiply all of these. -3 times 2 times 7 is -42. I have that a squared out here, and I have only the 2 left inside. If I were doing this one, I would just, again, use an easy prime. And go all the way down with that until I had all primes. Group what can come out. Those are groups. So 2 times 2 comes out. 5 stays in. And then in this case, no matter which way you do it, if you do it with your factor tree, u squared is u and u. So you have a u that comes out, none stay in. Or if you say, I'm going to take my exponent and divide by my index, that's 1 remainder of 0. You end up with u and v on the outside. Multiply 4uv square root of 5. So you can have a rather simple one, 56 and 14. And basically that's just the square root of 56 times 14. But instead of multiplying that and getting a large number, I'm just going to go ahead and do my factor tree for each of these. So I'm going to say, well, I can divide 56. That's divisible by 2. And so I can do that factor tree. And then I can do the same thing with the 14, right? And so with this, I'm going to, again, look at my index and say, well, I need to have them in groups of 2. So I have a pair there, that's gonna come out, and I can use anything. So this is a pair, right? So that's gonna come out, and actually this is also a pair. And so that comes out, and you'll notice I don't have anything left, right? So this is actually gonna end up being a perfect square. If I multiplied those two, I would get a perfect square, and I would say 2 times 7 times 2 is my answer. And so nothing stayed in the root there. My final answer is just 28. That can happen. So if I look at this next one, I automatically see I have something on the outside. So I'm going to go ahead and put that on the outside. I know that's going to be there. And then I am going to use my factor tree here. All right. And anything that pairs up in 2s can also come out. And so I have a pair of 3s, so that's going to come out, okay? And then I technically have this pair of 2s, right? It doesn't matter that they're in different groups here because I'm multiplying everything. So those 2s actually pair up. And the only thing that I have left in as far as numbers go is this 3 and this 5. All right. And then for my variables, I'm going to go ahead and combine them first. So p to the first times p to the third is p to the fourth. And again, you can do it however you want. You can just list out all 4 of those. Or you can do your division, 4 divided by my index. Either way, you're going to see group, group. 2 of my p's come out. Or if I do it this way, 2 remainder of 0. 2 come out. So either way, you're going to have 2 of those that come out, none that stay in. And then to finish this off, we are going to multiply. So we have negative 13 times 3 times 2. So I'm going to end up with negative 78 and that p squared here. And then 3 times 5, I'm going to end up with 15 on the inside. So with distribution, you are going to treat this exactly the same way we did the other one. So I am going to multiply, but remember you're going to compare if it's inside to inside, etc. So square root of 6 and square root of 12, I'm going to treat just like that page I just did. And then square root of 6 times square root of 6. All right. Square root of 6 times square root of 12, we have 2 times 3, 3 times 4, 2 times 2. Why does it keep doing that? That's weird. All right, so 2 times 2. All right. For this one, I'm going to group them just like I did. I have 2's there, I have 3's there, and I have a 2 that doesn't group. So for this one, I'm going to end up with a 2 on the outside, a 3 on the outside, and a 2 on the inside. And then make sure you bring down this plus, all right? You're not multiplying this one and the next one, you're adding them. So we have a plus there. Square root of 6 times square root of 6. This one's unique. You could do the factor tree here if you wanted to. But the square root of 6 times the square root of 6, we just talked about when we did rationalization. What happens when you multiply an exact radical, a square root by itself? It just becomes what's inside, because the square root of 6 times the square root of 6 is the square root of 36, which is always a perfect root when you do that. So this is just going to be plus 6. If you did your factor tree, you would get 2 and 3, 2 and 3, and you would have a pair of 2's and a pair of 3's that came out, which is 6, okay? So when it's something like that, that's kind of a special case with this, where you multiply a square root by itself. To finish this off, though, I do need to simplify these. So I do need to multiply this 2 times 3 and make that a 6. Plus 6. All right, here's the thing. For this guy, you cannot combine those. You can't add 6 squared to 6 plus 6. That's like adding 6x plus 6. They're not like, okay? So they're not like terms. And we're going to do some adding and subtracting later on. But they're not alike. We cannot add those radicals. And so we are done with this one. This is the answer here. All right, let's look at the next one. So I chose this one, obviously, because we have negatives all. All right, so I am distributing a square root. all right, specifically a negative. And I am distributing it first to a number that is not inside the square root. So I have to do two things here. I'm multiplying a negative and a positive, so that's going to be a negative. And I cannot combine those because one's on the outside. That 5 stays on the outside. That 42 stays on the inside. Now, we may be able to simplify him in a minute, but as far as the multiplication goes, I can't really do anything with the 5 and the 42. All right, and then I am distributing that negative 42 over here. Again, negative times a negative. What am I going to do? This is going to be a plus. That 2 is on the outside, and on the inside I have 42 times 12. And I'm going to leave him just like that because I'm going to do my factor trees for those because I don't want to multiply 42 and 12 personally. All right? And now, clearly that's not as simple as it will get. So I'm going to see if I can reduce. So for this 42, you may think maybe I can reduce him. Maybe something can come out. So go ahead and do the factor tree. You're going to see nothing actually pairs up. The square root of 42 is actually as simple as he gets because I have a 2, I have a 3, I have a 7. Nothing groups by 2. Nothing can come out of it. So this is as simple as it gets for this guy. 5 square root of 42. All right. Plus over here, I have a 2 on the outside, and I am going to do these factor trees here. 2 and 21. We already know what this looks like. We just did it. And then I have a 2 and a 6 and a 2 and a 3. Now I actually have something that can come out of this. I have this 2 already on the outside, so I don't want to forget that right there. Then I'm going to look and see what can group. So I have this pair right here that can group between all of them. So I have a 2. I actually have these 3s that group. See this? Those group, right? So I also have a 3. And then I have some things that do not group. I have a 2 and a 7 that do not group. So I'm only looking at my primes. Like I wouldn't say 21 didn't group because I already broke 21 down. I wouldn't say 6 didn't group because I already broke him down. We're only looking at my primes as far as grouping goes. And so this one actually had stuff that can come out. So I do need to simplify this with one more step. This is as simple as it gets. Negative 5 square root of 42 plus 2 times 2 times 3. That's 12. And the square root of 2 times 7, that is 14. And so this would be my final answer for this one. So my first step is literally to see, can I simplify anything first? Remember, you can reduce inside to inside, outside to outside, all right? So if the insides have something in common, you can reduce them like you would any fraction. If the outsides have something in common, you can reduce those like you would any fraction, all right? And so the first thing I'm going to look at is 16 and 20. Will those reduce, and if so, by what? 4. So I'm going to do this just like I would any fraction. I'm going to divide both of those by 4. So 16 divided by 4, that is just 4. It is still under the root. 20 divided by 4, that is 5. Now I'm going to say, can I reduce any of my radicals individually? Yes, one of those is a perfect root. Which one? The 4. So I can actually rewrite this to be 2 over the square root of 5. So that is really as simple as I can get it with what I've been given. Now I need to realize that to have it in true simplest form, I cannot have a radical in the denominator. And so I'm simply going to multiply the top and the bottom by that radical at this point. So I'm going to say, well, I'm going to multiply this by the square root of 5, and I'm going to multiply this by the square root of 5. The numerator is an outside multiplying by an inside, so it actually is just written outside, inside. We don't simplify them. The bottom, however, is a radical square root times itself. Anytime you multiply a square root by itself, what do you get?
5.
Just what's inside without the root. So on the bottom, I have a 5. Now here's the thing. Everything in you is going to want to reduce those 5s, but why can I not reduce those 5s? Yeah, they're not the same thing, okay? The square root of 4 does not equal 4. I can't reduce 4 and 4 there. That would give me 1. If you actually did it correctly, this would actually end up being 1/2, which is different than 1. So you cannot reduce outside to inside because they're not the same number at that point. 1 is the square root of the number, 1 is the actual integer itself, okay? And so we cannot reduce these. We are done here. Okay, makes sense? And then we have some variables. All right, so this next one, I have a 4 on the outside. I can only look here on the outside to see if it reduces, and it's a 1. So there's nothing I can do here. On the inside, I have a 5 and a 2. Those do not reduce. However, my variables can. Remember with variables, you can reduce 1 to 1, all right? So I have 3 m's on top and 2 m's on bottom. I can scratch out 2 of them, right? So I can get rid of all of the m's on bottom and all but 1 of the m up there, right? They reduce that way. If I were to write it out, it's m times m times m over m times m, right? With my subtraction method, I end up with an m on top, right? So then the n's kind of work the same way. I have 1 on bottom and 4 on top. I can reduce out 1 of them. So that's completely gone, and this becomes a 3. So basically, the only thing I can reduce here are my variables. I end up with 5mn cubed right there. And then right here, I'm going to end up with just a square root of 2, right? Now that I have this like this, and you could have done it before you reduced, it doesn't matter which way you do this. I look and see, can I simplify the radicals themselves? So I'm going to say, well, 5, that's not going to simplify. M, that's not going to simplify. What about n cubed? I have 3 of them. What is my index? 2. So for n cubed, that is n times n times n. I can group something and take something out, can't I? Yeah, I can actually take out an n. If you divided it, 3 divided by 2, that would be 1 with a remainder of 1. So I can actually rewrite this. I can take an n out, and I have 5m with 1 n left over, right? So when you're reducing these, don't only look at your numbers, look at your variables to see. And you could have actually reduced it first before you did top to bottom if you had wanted to. So if you had wanted to take that n to the 4th, you could have reduced that out. If you wanted to take the m cubed, you could have reduced. So you can always simplify your radical before you reduce up and down, or you can reduce up and down and then simplify your radical. It actually does not matter. You'll get the same answer, all right? But I do have one more step here. I can't leave the square root of 2 in that denominator. So I am going to rationalize this now that it is as simple as I can get it. This 4 and n are going to stay out there. Here I have 5 times 2. So I have a 10. And then I still have the m and the n in there. All over, anytime you multiply a square root by itself, you get what is inside. Am I done? I now have an outside and an outside that looks like it will reduce, right? Everybody see that? The 4 is on the outside. The 2 is now on the outside. 4 and 2 reduce. 4 divided by 2 is just 2, right? 1 on bottom, you don't have to write. If your 1 is the only thing on top, you have to write him. But if a 1 is the only thing on the bottom, you don't have to. So my final answer is going to be this 2n on the outside and 10mn left on the inside. And that's my answer there.